Okay, let's talk a little bit more about the Fourier transform. Mainly I'll do an example and go on to the fast Fourier transform. So let's recall where we were. We were talking about the interval from 0 to 2 pi, and we picked some integer n, and we broke this up to the points x0 through xn. And we had some function f of x, and we wanted to write f of x is approximately c0 omega 0 plus c1 omega 1 plus dot 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 c n minus 1 omega n minus 1, where omega k of x was the function e to the I k x. And the formula that we derived for the coefficients was that ck is equal to 1 over n times the summation from 0 to n minus 1. This is a summation over j of zeta n to the minus k to the j times f of xj, where zeta n is this nth root of unity, which is to say e to the 2 pi I over n. Okay, so let's just do an example, and this is the one I did in class, but I'll work it out again and finish it. So the example is I'm going to take n is equal to 4. So we're talking about these 4 points. This is 2 pi, and this is 0. And I wanted to take the step function. This is pi, and I was interested in taking the step function, which looks like this. And so the first thing that you do is you make this vector of values, the vector f, and the vector f is the vector of values at these points x0, x1, x2, x3, up to x4. It's the values at x0 through x3, and the values at x0 through x3 are these 4, which is to say 1, 1, 1, 0. And then you sort of prime the pump by computing these vectors, omega 0, the omega vectors, and omega 0 is 1, 1, 1, 1. And what's omega 1? Well, omega 1 is the values of the function omega 1 of x, which is e to the ix at these 4 so the example was n equals 4, and we were looking at the function on the interval from 0 to 2 pi, which was the step function. This is value 1. And since we had 4 points, the points are here, x0, x1, x2, x3, x4. And the value of the function was 1, 1, 1, 0, 0. So the first thing that you do is you make this value function for the vector, value vector for the function, which was 1, 1, 1, 0. It's a 4 vector. You go up to x3. You don't need the x4. And then you make these other vectors. So in this case, let's compute zeta n, which is to say zeta 4, which is e to the 2 pi I over 4. And if you draw a picture of the circle, which I always recommend, 1/4 of the circle is right here, and that's I, so this is the number I. And we make the following 4 vectors. Well, omega 0 is 1, 1, 1, 1, and omega 1 is the powers of zeta, which is, say, 1i minus 1 minus I. And omega 2 is the powers of zeta squared. Well, zeta squared is equal to minus 1. So you put minus 1, 1, minus 1, 1. And then finally, omega 4 is the powers of zeta cubed, which is minus I. So you're getting, excuse me, this is 1, minus 1, 1, minus 1. And omega 4 is 1 minus I minus 1 minus I. So here's what I just computed. There's F, and here are the vectors omega 0, omega 1, omega 2, and omega 3, and it's convenient also to compute their bars. So omega 0 bar is itself, and then omega 1 bar, you change some signs, and omega 2 and omega 3 bar looks like this. And then it's easy to compute the CKs. C0 is simply the inner product of F and omega 0 bar, which is to say, don't forget the factor of 1/4 out front, and you add up the first three coordinates, which is to say 3/4. And C1 is F with omega 1 bar, so that's 1/4. You add up those three coordinates and you get, excuse me, this is a minus 1, minus I. And C2 is, you add up these three coordinates and you get 1. And C3 is, you add up these three coordinates, and again, I forgot my minus 1 here, and you get I. And, sorry, I forgot my over 4. And so that says that this polynomial that I've computed is C0, which is to say 3/4, plus this constant, which is to say minus I over 4 e to the ix plus 1/4 e to the 2ix plus I over 4 e to the 3ix. And I said polynomial, but of course I mean this expression in terms of the exponentials. And well, I want a real valued function, so I need to take the real and take the real part of this. So let's expand this out in terms of its real and imaginary parts, which is to say 3/4. I'll write it like this way: 1/4. This is cosine plus I sine, so you get minus I cosine x plus sine x. And then here you get plus 1/4 cosine 2x plus I sine 2x. And the last term is plus 1/4. When you multiply in the I, you get I cosine 3x minus sine 3x. And so finally, the real function that you're interested in, I'll call that g of x, is the real part of this. And what's that? That's 3/4. What's the real part over here? 1/4 sine of x. And 1/4 cosine of 2x. And then finally minus 1/4 sine of 3x. And I'll just simplify that as writing it as g of x is equal to 1/4 3 plus sine of x plus cosine of 2x minus sine of 3x. So that is our approximation to the function given via the Fourier transform. So here's the answer. The function, recall, is approximately this sum, and so I've plotted each of the four functions separately. Here's the function 3/4, and here's the function 1/4 sine of x, and here's the function 1/4 cosine of 2x, and minus 1/4 sine of 3x. And when you add these functions up, you get the answer, which is this blue. And that's a reasonably good approximation to the step function, which was the constant function, and then it dropped to 0. And, well, of course, it's not that great an approximation because I've only used n is equal to 4. But you can see if you use more and more values, what happens is they sort of creatively interfere in this region to add up to 1, and they destructively interfere down in this region to add up to 0. Okay, so that's all I have to say about the Fourier transform itself. There's some discussion in the book about the problem of aliasing and noise reduction, but I'm going to skip that, and I'm going to go on to talk about the fast Fourier transform. So what this is about is a computational issue, which is that if you're trying to compute a Fourier transform with n steps, the number of operations that's required is what? Well, of course, there are n steps, and at each step we have to evaluate this sum, which is zeta to the minus kj f of xj, which has n terms in it, so there's approximately n multiplications. So, well, this is a very rough estimate, but you say basically it has n squared steps, n squared operations. And of course, as n gets large, this gets unwieldy. And the idea of the fast Fourier transform is to reduce the number of calculations required. And it doesn't, at first glance, it seems almost impossible to do this. I mean, you have to calculate all of these things, and there's, every one of them is some operation. It seems surprising that you can do it, but in fact, you can do extremely well, and it's in fact crucial for modern applications. People do Fourier transforms on huge data sets, and without the fast Fourier transforms, they'd basically be sunk. So let's talk about the fast Fourier transform, or FFT. And the basic idea is actually pretty simple, although its implementation is a bit intricate. The idea is the following. One of the main things you're doing when you're computing the Fourier transform is you're computing these powers, zeta n to the k minus kl, many times. And what you want to do is you want to speed this up. And here's a simpler example. It's essentially the same, but it's a little easier to think about. So let's do it. Suppose I asked you to compute 3 to the 64. So in this analogy, 3 is like this root of unity, and 64 is like this minus KL that you've got. So the obvious thing to do is you multiply 3 times itself 64 times. Well, how many operations does that take? It's 63, or that is to say approximately 64 operations. And here's a clever way to dramatically reduce that. Look at 3 squared. Okay, now take this number which you've just computed and square it. That's 3 to the 2 times 2, which is to say 3 to the 4th. And then do it again. 3 squared, squared, squared again is 3 to the 8th. And you just keep doing this, so you get 3 squared, that's 3 to the 4th, 3 to the 8th, 3 to the 16th, 3 to the 32, 3 to the 64. So, and how many operations is this? It's repeated squaring. You had to square a number which is 1, 2, 3, 4, 5, 6 operations. So this is the technique known as repeated squaring. And it makes computing powers much, much faster. Instead of 64 operations, I cut it all the way down to 6 operations. Well, what if I asked you to compute something else that wasn't a power of 2, like 3 to the 100? Well, what you do is you write 100 in base 2, which is to say it's 64 plus 32 plus 4. Or in binary, what is that? That's 0, 0, 1. That's 2 squared. And then 2 to the 5th and 2 to the 6th. That's the binary representation of 100. And so you say 3 to the 100 is 3 to the 64 plus 32 plus 4. And that's 3 to the 64 times 3 to the 32 times 3 to the 4. And you do each of these by repeated squaring and multiply them together. That is to say, you do 3 squared, squared, dot, 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 enough times to get 64. And then 3 squared, 2, 4, 8, 16, 32. And then finally 3 squared, squared. And this was 6 operations, and this is 1, 2, 3, 4, 5. And this is 1, 2. And so you add those up, and the total number of operations was 13. Whereas if you'd just done it directly, of course, the direct method cost you 100. So it's a dramatic savings. Now, how on earth are we going to use this in doing the fast to make in the Fourier transform? Well, we're going to do it when we have to compute these zeta n to the m's. And, well, it's quite an elaborate calculation, and the basic idea is the following, is this n you take to be a power of 2. That's kind of the key thing. And then, excuse me, I will illustrate this with r is equal to 3, so n is equal to 8, and we've broken up the interval like this, and what winds up happening is you first sample every other point, so you do 0, these 4 points, and these 4 points. And then out of the blue points, you group them again, excuse me, into these 2 points and these 2 points. And then similarly, the red, you group by these 2 points and those 2 points. And then finally, looking at the blue-green, let me circle those maybe. You're down here to blue-green. There's 4 of these pairs, blue-green, red-green, blue-yellow, red-yellow. And then this is the last step, is to just separate these 2. And when you break up the calculation this way, you're taking advantage of this repeated squaring idea. And well, I said it was intricate, so let's take a quick look at that. So the way it works is the following. We're trying to compute these CJs, and you compute them iteratively. You compute some intermediate guys, which are written C0J, and then you compute C1J, and eventually you compute RJ. And this is where n is equal to 2 to the r, and then this is the CJ that you want. So the number of steps is just r, which is to say log of n steps instead of n. And of course, log of n is much smaller than n. But in any event, I'm not going to write down the precise formula, but it's of the following form. Each c k plus 1 sub j is equal to 1/2 some c k some subscript plus some zeta to the something times c k some other subscript. So if you want to see the exact formula, it's 5.119. But for now, I'm just going to show you the form of it. Each CJ at the k plus 1th step up here is a sum of two C's from the preceding steps, and exactly which C's are given by these dots. And also there's a power of zeta which comes in, and that's how the calculation proceeds. So let's just do this example. Well, I should say there's an example in the book, which is 5.63, and I'm going to do the example that I did before, which is just with n is equal to 4, and it's this step function that I was doing before. So here we go. Okay, so here we go. So remember that the f vector that we had was 1, 1, 1, 0. That's these three values, 1, 1, 1, 0. And the first thing that you do is you have a permutation of this vector. And the way you get the permutation is you write down the numbers 0, 1, 2, 3 in binary. And then you reverse the order of the bits to get 0, 0, 1, 0, 0, 1, 1, 1, which gives, and then you convert back, which gives 0, 2, 1, 3. And so this f prime is the values of the f's in this order: f0, f2, f1, f3, which in this case is 0, 2, 1, 3, 1, 1, 1, 0. So in this case, it turns out to be the same, but okay. And I'm going to make a little chart. What happens is I'm going to start with, I'll just indicate it here, 1, 1, 1, 0, and then I'm going to get, these are the C0Ks, and then I'm going to compute the C1Ks, and then I'm going to compute the C2Ks. And since R is equal to 2, that's the answer. So here's how it works. This is the 0th level, then the first level, and then the second level. And on the first level, the thing that you need is the relevant. There's a number 2 to the 1, which is equal to 2, and zeta 2 is equal to the square root of 1, which is minus 1. That'll be playing a role. And then here you have 2 to the 2 is equal to 4, and zeta 4 is equal to I. That's also going to be playing a role. And what happens is the following. So I'm going to indicate the 4 steps according to these color codes. So the first step is you do these two with a plus, and the second step is you do these two with a minus, and the third step is these two with a, excuse me, that should have been green. These two with a plus, and then the final step is these two with a minus. And what that means is for the first step, I add these two with a plus sign, and there's always a 1/2. So what you get from the first step is 1/2 1 plus 1, which is equal to 1. And the next step is 1/2 1 minus 1, which is equal to 0. And the next step is 1/2 the sum of these, which is equal to 1/2. And finally, 1/2 the difference of these, which is equal to 1/2. Okay? And this minus is this minus. Okay, now the next step, what we're going to do is we're going to be using powers of I, and the order that you do things is different. This was the first step, and I was adding and subtracting things which were 1 step apart. This is the second step, so we're going 2 steps apart, and what you get is these guys with a plus, followed by these with an I, followed by these with a -1, and finally these with a -I. And that's these numbers are the powers of I. 1I minus 1 minus I. And what do you get? So the first entry is 1 plus 1/2. Let me write it over here. The first entry is 1/2, 1 plus 1/2, which is to say 3/4. And the next entry is 0 plus I times 1/2, which is to say 1/4 I. And the third entry is 1 minus 1/2 times I. Excuse me, 1 minus 1/2. Write it down. The third entry is 1 minus 1/2, which is 1/4. And the final entry is 1/2, 0 minus I times 1/2, which is minus 1/4 I. And, well, sorry for the colors here. It's maybe a little garish, but this is the answer. So C0 is 3/4, C1 is I over 4, C2 is 1/4, and C3 is minus I over 4. And that's exactly what I got doing it the previous way. And let's just look at how many operations it took. So remember, here we were talking about n is equal to 8, which is equal to 2 cubed. And it only took me 2 operations. Excuse me, n was equal to 4, which is equal to 2 squared. That's more like it. And so the relevant number here is 2. It only took me 2 operations to compute this 3/4. I did this one here, and then this one here, and so on and so forth. So the fact, which is basically sort of clear from everything I've said, is that the number of operations required for this is approximately n log n, which is dramatically less than n squared. So this is much less than this because if you cancel the n's, this is just saying log n is much less than n. And that's true. Log grows incredibly slowly. It's the sort of opposite to the fact that exponential grows incredibly fast. So just to give you the idea, let's look at this number here. When n is equal to 1,000, I'm saying that the left-hand, this side is approximately 6,900 compared to 1 million. So you can compute the Fourier transform in about 7,000 steps instead of a million. And when n is 10,000, the inequality is, the left-hand side is 92,000, which is dramatically less than the right-hand side, which is 100 million. And so you can see clearly that as n gets bigger, the savings in doing the fast Fourier transform is enormous. And in any practical application of this stuff, you always use the fast Fourier transform. And let me just conclude by a little something that you can look at. I'll just write it over here. See F, 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 T, W. And I have to mention this because it's a great fast Fourier algorithm and it has a wonderful name. This is the fastest fast Fourier transform in the West. Okay, so that's all for now, and have a great Thanksgiving. We'll see you on Monday. And let me remind you that there will be another video for viewing on Monday.